Okay, we're on to chapter 10, where we're going to stick with hypothesis testing, and we're going to move on to working with just one sample and one parameter to two samples and two parameters. So in chapter 9, our goal with hypothesis testing was to determine if a mean or proportion was equal to some fixed value. One of the questions we asked was, does the population mean by state tuition for private universities, that is mu, equal $20,000? So we were testing about the population mean, and the fixed value that we were asking if it was equal to is $20,000. And we did a test with the null hypothesis of mu equal to $20,000 and the alternate hypothesis of mu not equal to $20,000. So to answer that question and to do that hypothesis test, we had one population, the population of states, and we had collected the data of mean private university tuition, and that made up our sample. Now in chapter 10, we're going to now look at two parameters, and we want to determine if the parameters from two separate populations are equal. Often studies are going to compare two groups. You see this over and over and over again in all sorts of studies and reports that are done. So let's look at an example. Suppose researchers are interested in looking at the effect that aspirin has in preventing heart attacks in patients with heart disease. So we might conduct a study and break our study subjects up into two groups. One of those groups would be given aspirin. We'd call that the experimental or treatment group. And then the other group is not given aspirin, but maybe given some other placebo, something that they don't know what the effect of it is. We call that the control group. And the heart attack rate for these two groups is recorded and tracked for 10 years. So then we can ask the question, is the mean heart attack rate for the treatment group, we'll call that mu1, equal to the mean heart attack rate for the control group? We'll call that mu2. Okay, so here we are comparing two means, and those means come from two separate populations. Okay, we have the group that has the aspirin, that's reflecting the population that takes aspirin, and then we have the group that doesn't take aspirin, takes the placebo, and that represents the population that doesn't take the aspirin. All right, so we're wanting to compare the mean heart attack rate for these two populations. So now we got to revise the way that the hypotheses look. So the null hypothesis is that there's no difference in the means. So it's mu 1 equals mu 2. All right, that means that there's no difference. Now the way that it's typically written is not that they're equal, but we look at the difference between those two. So if we write it as the difference between mean 1 and mean 2, we get the null hypothesis is mu1 minus mu2 equals 0. Okay, for the hypothesis test we do in this chapter, we're going to follow the exact same 4 steps. So, like we have seen, the hypotheses are going to look a little bit different. The other thing that's going to be different is the test statistic. Okay, so we will get to that as we get to the different types of tests, but just keep that in mind. We're following the same 4 steps. All right, the hypotheses, the test statistic, the p-value, and the conclusion that we did in chapter 9. So the differences are in the hypotheses and in the test statistic. Okay, the different kinds of tests that we're going to look at. First of all, we're going to look at a test of two population means from independent group samples. That is what that example just reflected. Okay, we looked at two different populations. They're totally independent of each other, and we're comparing means. All right, we can also have that same scenario where we have two different populations, but instead of comparing means from those two different populations, we're comparing proportions. Okay, that will be in section 3, and then the means was section 1 and section 2. Now, the other kind of test is if we've got what we call matched or paired samples, where the samples are dependent. One way to think of that about that is if we just have one population and we measure two different things from that population. And so we have two variables. So we have one population, two variables, we get a means from each of those variables, and then we compare those variables. That's going to be the other kind of test that we do. Okay, so let's start off with this first kind of test where we're going to take two population means, and we either have known or unknown standard deviations. It's the same thing as when we were looking in chapter 9, where if we know our standard deviation from the population, we can use Z. And if we don't know that, or we have a small sample size, then we use T. We have the same scenario going on in this chapter as well. Okay, so let's look at some data collected from this study from the example, where we're comparing the mean heart attack rate for an experimental group, which has size 15, and a control group, which has size 20. So the experimental group is the one that had the aspirin. So we want to test if the mean rate for the experimental group is less than for the control group. Okay, so for the experimental group, we have sample size of 15, sample mean heart attack rate. So per patient per year over the 10 years is 0.067. And then our sample variance is given, sample standard deviation. And then for the control group, different sample size. There's 20 in the control group that did not take the aspirin. And the mean heart attack rate is 0.095. And then you see the variance and the standard deviation for that sample. Okay, to do this kind of test, it requires that we have two samples. They're independent. They're taken from two distinct populations, meaning you can't have one member that could potentially be in both groups. Okay, they have to be completely distinct. All right, then we have two population means that we're testing. All right, one from each of the populations, mu1, mu2, and then we have x bars from each of the samples, x bar 1, x bar 2. And the sample variances are S1 squared, S2 squared, and we have two sample sizes, N1 and N2. Okay, so the steps are, first of all, we're coming up with the hypotheses. Okay, the null for this kind of test is always going to be one of these two things right here. Okay, that those two population means are equal, that there is no difference. Okay, so there's no difference. And then the alternate is going to be that there is a difference, and then we can specify what kind of difference. So if the difference is that the first mean is greater than the second mean, okay, like we have in this first line, then the alternate is if we take the difference between those two and the first is greater than the second, then the difference is going to be greater than 0. And if the second scenario, if we are testing that the first mean is less than the second mean and we take the difference, then that difference is going to be negative. It's going to be less than 0. And then if we take in our testing that the means are just not equal, then the difference is just not equal to 0. So in our example, we're wanting to test if mu1 is less than mu2. Okay, we can always start off by writing it that way, but then we want to write it in terms of a difference. So the alternate then is the difference, mu1 minus mu2. Okay, well, if mu1 is less than mu2, then this difference is going to be less than 0. Okay, so that's our hypothesis for our example. Now let's look at the other thing that's going to be different from other tests we've done, and that's the test statistic. So we got to determine what distribution we're using. If we have small sample size, they're both less than 30, and we don't know population standard deviations, and they're not equal, then we can't assume that normality, and we can't use normal, so we're going to use the t-distribution. Most of the time, we're going to be using the t-distribution. So we're wanting to estimate this parameter, the difference in the means, and so we're going to estimate that with the difference in the sample means. Okay, the test statistic that we're going to use is listed there. So in the numerator, we have the difference in the means. And now what's missing there is that we're really subtracting that 0. Remember that 0 is from the null hypothesis. We're in the null hypothesis, we are assuming, to do the test, we're assuming that this difference is 0. So if you think back when we did hypotheses, the hypotheses for the single population tests, the value that showed up in the hypothesis always showed up in the test statistic. Well, it's showing up here too. It's just 0, so we don't list it. Okay, so we have that difference in the sample means in the numerator, and then in the denominator, we're finding a variance, or I'm sorry, a standard deviation or standard error to use. Okay, so we take, notice that it's variances here, variance from the first sample over the sample size plus variance from the second sample over the sample size. So for our example, we are going to get a t-statistic of, in the numerator, we take the x bar from the first sample, 0.067, subtract x bar from the second sample, 0.095. Okay, divide that by, we take the square root of, okay, first variance, 0.009, divided by 15. Plus the second variance, 0.012, divided by a sample size of 20. Okay, let's round this to 3 decimal places. And we get negative 0.808. The next step in hypothesis testing is to find the p-value. Okay, so we're going to use our online tool to find that p-value for our test statistic. One other difference here is finding the degrees of freedom. To find the degrees of freedom before, we would just take the sample size and subtract 1. Well, we have 2 sample sizes, and it's a little more complicated to find the degrees of freedom. So the degrees of freedom is given by this formula right here, which it looks much worse than it is. So let's calculate that. All right, so in the numerator, we've got the standard deviation of the first sample, 0.009, over the sample size, 15, plus the standard deviation of the second sample over its sample size of 20, and then that whole thing is squared. And that's divided by that sample variation, 0.009, over sample size of 15. That quantity is squared, and then it's divided by 15 minus 1, 14. Okay, then we do that same thing for the second sample. So 0.012 over 20, that squared, divide that by 19. Okay, this is pretty easy to plug into your calculator just all at once. You can just get that numerator, and then you use some parentheses and divide by that denominator. And we end up with 32 point, actually it's, I think, repeating to 4. So it's not an integer. We need degrees of freedom to be an integer. We always round down. So it doesn't matter what the decimal is, even if like that first number is greater than 5, we're going to round down. So round down to 32. So that can be used to find the p-value from the online calculator. And if we plug in that test statistic of negative 0.808 for 32 degrees of freedom, we end up with a p-value of 0.2125. Okay, so I want to hold on just a second here before we go on to the conclusion. So the things that have been different so far are the hypotheses, and then the test statistic, and the degrees of freedom. Okay, and you notice we're following the same pattern, and we can just follow the same pattern here for the conclusion as well. Okay, so we have our p-value 0.2125, and I don't think we specified what our significance level is for this test, but 0.2125 is greater than any of the significance levels that we would use. So doesn't matter which of those three, we are going to not reject the null hypothesis. Okay, so for this example, we're not rejecting that the mean heart attack rate for these two groups, those that take aspirin and those that don't. We're not going to reject that they have the same heart attack rate. We're going to do another example of this type of test. Go ahead and read that example and then pick up after that. Okay, so I have a little chart here to help us identify all the pieces that we're going to need. We have two different populations. One population is beverage A, and the other population is beverage B. And there's a sample size from each of those populations. From beverage A, we've got sample size of 13. Sample mean for beverage A is 36. Sample variance is 0.36, which we get by taking the given sample standard deviation and squaring it. For beverage B, sample size is 6. Sample mean is 38 grams of sugar. Sample standard deviation is 0.8, so squaring that we get sample variance of 0.64. So we want to go through the 4 steps. So first step is the hypotheses. Now, the null is always going to be mu1 minus mu2, or we could just even label these as mu a minus mu b equals 0. Okay, so mu a is the true population mean grams per sugar of beverage A, and then mu b is the same thing for beverage B. Now is the alternate hypotheses. So we're testing, or the researchers believe that beverage B has more sugar. So they believe that the mean for A is less than the mean for B. So in terms of a difference, the null hypothesis, or the alternate hypothesis, is mu A minus mu B is less than 0. Okay, so now we want the test statistic. All right, our sample sizes are less than 30, and we do not know the population standard deviation. And even if we did and they weren't equal, we would still have to use t. So we're going to take t equal to, all right, the difference in those sample means, 36 minus 38, over the square root of sample variance for A, 0.36, over sample size 13, plus variance for beverage B, 0.48, over sample size of 6. So calculating that, going out to 3 decimal places, we get negative 5.456. So the next step is to find the p-value, but to do that, we need the degrees of freedom. So plugging things in, okay, in the numerator we get 0.36 over 13 plus 0.48 over 6, that whole thing squared, and then divide that by 0.36 over 13, that squared, divided by 12, plus 0.48 over 6, that squared, over 5. And that's going to give us something like 7.7, but we round down and we get degrees of freedom of 7. Okay, so we have to remember when we go to that T calculator that we've got a left-tailed test. So we're looking for area to the left of the T statistic of negative 5.456. So if we look for that value using our calculator, we get a p-value equal to 0.0005. Okay, now again, using any significance level, we're going to come to the same conclusion. All right, we are going to reject the null, and that is because the p-value 0.005 is less than alpha at any level, 0.01, 0.05, and 0.1. All right, so we're rejecting that these two drinks, these two beverages, have the same sugar content.